Given image is a Bohr's atomic model of nitrogen atom where you can see a neutron and electrons in their orbits. The neutrons consist of nucleons, which is protons and neutrons. Neutrons are chargeless particles, whereas protons have charge, a positive charge. We have learned in electrostatics that same charges repel each other and opposite charges attracts. So, in that case, have you ever wondered how does a proton which is having a positive charge stay together inside the nucleus? A nitrogen atom is having 7 protons and 8 neutrons inside the nucleus. So, there should be a force which is acting somewhere in the nucleus that holds the positively charged protons without repelling each other. Let's dive in. What is a nuclear force? It is the attractive force which is acting between neutrons and protons inside the nucleus which holds them together. It can act between proton-proton, neutron-neutron and neutron-proton. Protons have positive charge and they experience an electric force and tend to repel each other. But nuclear force is strong enough to overcome the repulsion due to electromagnetic force and hold them together. So, it is basically the nuclear force binding the nucleons in the atomic nuclei. Since neutron has no charge, only nuclear force is acting, whereas there will be both electrostatic force and nuclear force between protons. Nuclear forces are of two types, namely strong nuclear force and weak nuclear force. Strong nuclear force holds the subatomic particles of protons together and also the nucleons together. Weak nuclear force is responsible for the disintegration of matter. It is observed during radioactive decay of certain nuclei. In order to break the nucleus into proton and neutron, we need to supply energy to the nucleus. The energy required to break the nucleus into its constituent proton and neutron is called the nuclear binding energy, or in other words, it is the amount of energy liberated while combining individual protons and neutrons into a single nucleus. It may be expected that the mass of nucleus will be equal to the sum of masses of protons and neutrons. But in reality, the nuclear mass m is always less than the sum of the individual masses of protons and neutrons. The difference in nuclear mass and its constituent is called mass defect, denoted by delta m, and is given by the equation delta m is equal to Zmp plus A minus Z Mn minus m. Since the nuclear mass is less than the sum of constituent masses, the equivalent energy of nucleus will be less than the sum of individual energies of its constituents. So, there is a difference in energy, and this extra energy is to be supplied to break the neutrons, which is the binding energy, or if we combine protons and neutrons to form nucleus, this much energy is released. It is obtained by Einstein's energy equation EB is equal to delta mc square, where delta m is the mass defect, A and Z are the mass number and atomic number respectively. Capital M is the mass of atom minus mass of electrons, and EB is the binding energy. Binding energy curve is an indicator of the nuclear stability. It is plotted between binding energy per nucleon, which is the average energy per nucleon to separate a nucleus into its individual nucleons, to the mass number A. The binding energy increases up to iron, which has an atomic mass of 56, and then decreases for heavier nucleus. It remains almost constant for the middle mass numbers with mass number between 30 and 170, from which we can conclude that binding energy per nucleon is independent of atomic number. For iron, the binding energy per nucleon is maximum at 8.7 mega electron volt and decreases after iron. You can see it here. For elements having a mass number more than 200, the binding energy per nucleons is around 7 mega electron volt and they show radioactive behavior. and when disintegrate into lighter elements, the nucleons are tightly bound and energy is released through fission. For a lighter nucleus, when combining to form heavier nuclei, binding energy per nucleon for the combined heavier nuclei will be more than individual lighter nuclei, and thus the final heavier nuclei are more tightly bound and energy is released through nuclear fusion. Now, let's see the properties of nuclear force. Nuclear force is attractive in nature, which is the reason why nucleus is held by itself without collapsing into its constituent components due to electrostatic repulsion. Nuclear force is a short-range force, which means it falls into zero when the distance between the nucleons is more than a few femtometers. At a distance greater than 2.5 femtometer, nuclear force literally does not exist. Here, the plot shows that the potential energy is minimum at a distance of about 0.8 femtometer. The force is repulsive for a distance less than 0.8 femtometers, which actually affect the size of the nucleus. The nucleons comes closer to each other till a point after which the repulsive force will not allow the nucleons to come closer. Next point, nuclear force is identical for all nucleons, whether it be proton-proton, proton-neutron or neutron-neutron. Most common example where nuclear force acts are the binding of nucleons. While on a larger scale, strong nuclear force is responsible for nuclear fission, which is used in nuclear reactors and nuclear weapons. Weak nuclear force come into play during the decaying of certain nuclei and also used in radiocarbon dating. Now, let us summarize what we have learned so far.
Manorama Horizon, learning made simple.